Hi everyone, I just wanted to give you a brief introduction to my brand new CNC machine. The CNC machine is constructed primarily out of 80/20 aluminum using 20/20 and 20/40 brackets. And then all of the linear motion is achieved using Thompson Industries Rapid Track linear actuators. So let's get started. The first thing I did to ensure that I had a very rigid machine was start with a very rigid material, extruded aluminum. I had 80/20 cut all of this aluminum to size for me, so that it was pretty simple. Just take it out of the box, assemble, checking for square. And then I had to figure out how I was going to take these Thompson Industries about 19.5 inch of travel rapid track linear actuators and attach them to the 80/20 that I was using for the structure of my machine. The way I chose to do that was simple 3/4 inch Mike 6 aluminum plates. So essentially what I did was I would mill out a plate that was just 4 holes in a 1 inch square pattern, a bolt pattern, that could pick up these 80/20 aluminum brackets. And then on the back end, I would have 3 holes that were placed about 3/8 of an inch away from the actual actuator on either side that could then take these custom milled clamps to clamp these actuators directly to the brackets that I milled using the T-track that is inherent in the extrusion of the actuators themselves. So these linear actuators are based upon Prism linear guides. So the veteran CNCers out there will know that this is definitely not an ideal situation, because normally you want to be using at least 4-point ball bearing linear slides, such as like the THK slides, that will allow maximum rigidity from the bearing itself. However, in order to overcome this complication, what I did was multiply the number of slides to achieve the number or the amount of rigidity that I desired. So on the y-axis table, for instance, of course this is a fixed hamstring machine, what I did was instead of using one slide and then expect to be rigid all the way out 10 inches from that single truck on these rapid track slides, I instead used 2 passive actuators and 1 driven actuator. I acquired all of these linear actuators off eBay for about $120 a piece, so it was actually a pretty good deal to acquire decent linear actuators with a fairly good rigidity. These units are ball screw, so I believe that they're 5.08 millimeter pitch ball screw. Unfortunately, they are rolled ball screw, so that does mean that there is backlash in the system. I believe that the X and Y axes both see about 0.03 of an inch of backlash, which is about what I expected. And the Z axis, which has 2 independent actuators that are slayed together to carry this X carriage, sees no backlash because of the gravitational effects. I've also tried pushing up on this, just putting a dial indicator on top, and I still haven't been able to measure the backlash this way. So using these Prism guides, I'm sure a lot of you are curious about the rigidity of this machine. So why don't we just go ahead and test that real quick. So we'll just drop the machine down using my little pendant here. And then I have a Michi Toyo dial indicator on a Nogo base. So I'll just go and put this right here. And this is the weakest point, bear in mind, in the entire build. So if I put most of my weight here, I see about 6 thou deflection, and I mean that's the majority of my weight. And this is the weakest point because these actuators are very bad at dealing with forces that are perpendicular to their motion. So like if I'm going up and down, which is the force that's primarily seen on this x-axis, that's where the actuator is going to be the least capable of dealing with all of those forces. Unfortunately, I originally had a design that incorporated 1 fewer linear actuators. And essentially this X-carriage bridge and this kind of fixed gantry system, it only had 1 actuator. But the reality was it just wasn't rigid enough to stand up to the forces that I needed. Doing that same test, that is creating about 5 to 6 thou deflection by putting my body weight vertically onto the router right here, would create about 20 to 30 thou deflection. And for me, when I can physically see the deflection on any one of my machines, that's a big warning sign that I need to figure out a new way to make that machine much more rigid. And luckily for me, adding a second passive actuator, just by purchasing an additional one of these actuators off eBay and ripping out the ball screw to create a passive one, provided me with the fix I need. Here on the table, I see about, I can't really measure because of these plexiglass side panels I put on either side, but I see 0 deflection perpendicular to, putting my force here, I see 0 thou deflection on the table side to side. Front of back, you still see that the 3 thou backlash, but other than that, it's very good at dealing with deflections in that regard. All the aluminum here that's not 80/20, I should mention, is Mike 6 or some other kind of ground cast tool plate. So I use that in order to ensure maximum parallelism and flatness. So on this half-inch piece of Mike 6, for example, I believe there's 5 thou or less deviation across the entire surface, and that's in both thickness and parallelism. So that ensured that I would get my machine within tolerance for what I wanted to do. One thing that's kind of unfortunate for how I built this machine is all of these Mike 6 or other type of cast tool plate that pick up these Thompson Industries linear actuators, unfortunately don't have any positive locking motion in them. Because of the means that I fabricated these plates through, essentially what I would do is I would cut out a piece on my CO2 laser system and then drill through using that template in order to ensure it was as accurate as possible, and then cut out the actual piece on the table saw. Because my only other machine that can cut out aluminum using CNC capabilities isn't in this location right now. So I was just using my table saw and a drill press to fabricate all these parts. But by using that template system, I was able to maintain about plus or minus 5 thou of accuracy. So what I did to actually locate them then was essentially just ride these dial indicators up and down to ensure that all of these parts were parallel and all of them were the correct distance apart. And before I did that, I just used a rough laser cut template to ensure that these were as accurately placed as I could get them before I started to bring in a dial indicator to really get everything close. One thing you might also notice is this system uses exclusively servo control. So I'm using Technic servos. I know a couple other people have done that. I know David from Neo 7 CNC uses similar Technic ClearPath servo motors. And I've seen John from NYCNC use them in projects as well. They're very nice because you put out a lot more torque with the servo motor, and of course it's a closed loop system. So assuming that you don't see any backlash on your couplings, and or if you're able to measure out your backlash in all of your actual axes, then what you can do is ensure that you're never going to miss steps like you would in a stepper system. They're also very nice because this is a very compact system. They're all on a NEMA 23 frame size, but they have a lot more torque than a standard NEMA motor. I'm not exactly sure what the max torque on these ones is, but I know that these are capable of a heck of a lot more than the NEMA 24 on NEMA 23 servo, or steppers rather, that I've used in the past. This also ensures that the machine can move as quickly as I want to move it, because I didn't want another machine that had very slow rapids. This is my 4 CNC machine, and the first and second machines moved very slowly, and then the third machine was the THK KR33 machine that I based mine on off of David from Neo 7 CNC, and that machine had great rapids. However, its capacities were so small that I was finding myself underutilizing that machine, so I just converted it to a 3D printer and starting to use this one for CNC capabilities. So this machine gets about 400 inches a minute of rapids, which is satisfactory for me, and about what I would expect out of a Prism Guide rolled ball screw system. I've also done some creature comfort modifications to this machine. For instance, there's this little pendant holder. So I would find myself always kind of hunching over using my keypad in order to, like in step mode in Mach 3, in order to ensure that I would get as close to my part from my 000 position with my G54 work offsets as I could. But it was really inconvenient, so I found that having a pendant would really improve that. And one thing you can do is you can take these little Logitech controllers. I know people use Xbox 360 and even Xbox One controllers as less expensive pendant options that are still quite convenient. And the nice thing about this system, you can find the macro for it on the Mach 3 Newfangled Solutions website. And it allows you to button map basically everything on the controller. So if I hit left on the D-pad, for instance, it'll move my jog speeds down in increments of 5%. If I hit this back button, it can stop the program. If I hit the start button, it can start the program, and so on. One additional creature comfort that I added to this machine is this nice computer stand. So I'm sure that a lot of CNCers out there will point out, well, what the heck, why is this guy using a Windows 10 laptop to run a CNC machine? Well, the reason I'm able to do that is because I'm utilizing a UC400 Ethernet control system. So that's really nice because not only does it have all the timing external to the computer itself, but it also allows me to run 2 parallel port boards and then move that all into essentially any PC, because all the real-time operations are controlled by a timing board on the UC400 Ethernet controller. So basically what's happening is we send this downstream, the timing board's there, and then I can send it out to 2 further breakout boards, also meaning that I have a lot of additional I/O. So it allows me to get in a very convenient package, at least for my computer system, that's completely external and optically isolated from the system that I'm using in my CNC machine control, which can avoid a lot of unnecessary complications in the future as well. So one other thing that I added that is a very nice feature on this machine is an automatic touch probe. So one thing that's kind of unfortunate about how this machine works, and I didn't find it out until after actually using it for a while, was that the way most auto touch probes work is in your inputs on one of your breakout boards, you'll have one pin going to that input and one pin going to ground. And whenever you connect that signal, what will happen is it'll stop probing, it'll stop probing the bit, and then it'll lift up, accounting for the offset of your plate. What this means is that if you have a machine that is mostly aluminum and heavily grounded everywhere like mine, you might end up accidentally grounding almost immediately. So what I would find is if I just put this plate on the table, and I just put my alligator clip that has the second connection, because this router isn't grounded all the way through, right here, I mean at least not consistently grounded all the way through, when I auto probed, it would just trigger early for some reason. So what I do instead is make sure that the material I'm using is non-conductive, and if it is conductive, I have to use a shim and modify my macro to account. But usually that's not happening unless I'm milling aluminum. So for instance, if I grab this fixture plate with a job I was working on earlier, grab an impact driver just to drive it down temporarily for demonstration. Now, because I'm not grounding this all the way through unnecessarily, I can use my auto touch probe. So normally what I would do, if this were aluminum for instance, because I do mill a lot of aluminum on this machine, is I would put a piece of paper under this and then account for that 5 thou offset, either directly in Mach by just typing in the value that I'll move to. So instead of typing in 1 inch, I could type in 1 inch and 5 thou, or alternatively I can just go in directly with the macro and change the thickness of this plate. So what I do is hit Auto Tool 0, making sure that I have both the bit and my grounding plate plugged into the CNC controller, and of course working in the diagnostics tab in Mach so you don't crash the machine. And then I wait, and it comes it down at 4 inches per minute. This was what I found. I found this, I believe it was CNC Guru Brew. It was the macro I was using, and essentially, other than the dwell time, reducing that a bit, because my CNC computer is right here, it's pretty much unmodified, so that macro has worked out very well so far. Once it comes down and ground, it'll come back up to a set position of 1 inch, so you have access to the bit. And it's grounded. So now we're at auto 0, or I mean we're 0, using the auto 0 command. So if I 0 x and y, just in my DRO, and tell it to go to 0, I should be able just to wrap it over everything. Just essentially being a very, very, very small distance between the workpiece. So the way I actually configured my plate was by configuring the plate about 3 or 4 thou under thickness, you can ensure that you won't skim cut your material on accident. when you're doing things like trying to get into your 000 home position that you set in cam for your stock. So for instance, let's say my 000 is in the center of my workpiece like I normally do. So this X on the center of this blank right here. What I would normally do is I'd use my pendant to go up and then down right here. And of course I'd be using Auto Tool 0. But in this exact situation, what could happen is if this were at exactly 0, but there were small deviations either in my part or a small amount of air anywhere in the machine, if I were to then wrap it at the 0 plane, which you should never do, you should have clearance planes, but I mean there are some issues with Mach 3 to where that can happen. For instance, when I didn't have homing switches, it didn't know where to go in my homing system, and that actually turned out to be an issue with me homing it exactly on the top of the part. So tool changes would occur exactly on the top of the part, therefore causing it to wrap it exactly at the Z0 height in machine coordinates, which happen to be the top of the part exactly, resulting in an unnecessary skin cut. So one thing I'd like to do is just show you some sample G-code and how this machine operates. So if I put all my work offsets to 0 and then rewind this sample G-code, it'll go to the absolute coordinate -9 with 0 being right here and wait for the first tool change. This is something I'm trying to get better at, is configuring Mach 3 in order to ensure that my tool changes are as efficient as possible. For instance, when I'm doing a job, my first tool change I will have already done before setting up the job, because I usually immediately cam in the same room before and then put the tool bit in and then zero everything off of that tool bit so I don't have to do additional work zeroing. So I'd like to ensure that my first tool change command, I can either omit that in my post or otherwise edit it so it doesn't go to my height for tool changes. But then when I start that, it'll start the spindle, and of course I don't have this router relay controlled yet, so it won't actually start the spindle. I have to manually do that. And then it'll begin cutting. So this one just has a short, probably 20 seconds run through of simulated cutting. And then it goes back to its tool position, which is an absolute coordinates -9, because I have a homing with Z0 at the top, and then as far as it'll go is like Z-17, because this actuator comes down here, and I have a little additional distance left there for when I choose to do a 3D printing modification to this machine. A lot of you are probably wondering, well, it doesn't make a lot of sense to have an 18.5 by 18.5 by 18.5 work area. Of course, your X and Y coordinates being that large makes sense, but in this kind of small format machine, why use up all this additional space, making sure that you have just kind of ridiculous Z capacity? And the reason for doing that is I plan to change this into a 3D printer in the future. And I've equipped this machine with a lot of the potential I/O to do that. So in order to ensure that I'm able to change this out between a CNC machine and a 3D printer, I have to make sure that it can move fast enough to be a 3D printer, but at the same time it has enough stiffness to act as a CNC machine. Because obviously to cut aluminum well, I can't have large deflections, but obviously to 3D print, I need to be moving at a sufficient speed, which may be upwards of 100 millimeters per second, if you want to have a reasonably fast print speed. So what I've done is use a system very similar to normal 3D printers. So like consumer 3D printers such as like the Lulzbot Mini or the Taz machines or a lot of other machines, what they'll do is they'll have two independent lead screws that move the Z-axis that has the X carriage on it, and then move the bed front to back, exactly how this machine operates. That's ideal for me in a CNC situation because I can get maximum rigidity having this kind of pseudo fixed gantry system while having a moving bed, and it's also ideal in a 3D printing system because it allows me to stay rigid for CNC applications while giving me the capacity I need for the actual 3D printing. In the control box itself, the use of a UC400 Ethernet controller, like I mentioned earlier, gives me two independent parallel port controlled breakout ports, meaning that I have the I/O sufficient to run, I believe, 7 different motors. And normally, you would think you only have 6-axis control in Mach 3, which is true, But I was having so many slaving issues with these two independent actuators that were slaved in Mach 3 with soft limits enabled, as in the issues weren't arising until I started to use homing and soft limits, that I eventually just opened up the controller, took out my A-axis, which was this left system right here, and then wired it directly into the same pinout rather, that's controlling this other Z-axis. So now, with this new system, I've expanded capability for 3 additional motors. So in this somewhat large, moderately rigid system, I'm able to now also add things such as a 5-axis auxiliary, potentially add something like a tool changer in the distant future if I ever change to something that's not exactly a woodworking router. And of course I also have the I/O necessary to drive the couple different axes necessary for 3D printing through Mach 3. The way I've been controlling that in the past, because I made this modification to my THK KR33 design based on David's from Neo 7 CNC, was in Mach 3 I would go into my A-axis and I would set that as the extruder axis. And then externally I would have something like a Rambo board or some other, like a smoothie board, some other kind of 3D printing control system, and through there I would run all the PID loops. So I would have complete PID control through just an additional USB port coming from a Rambo that would have my control for both the heated bed as well as the extruder itself. So I could then just independently set those temperatures manually and then run it in Mach 3, the program for 3D printing that is, as if it were just normal G-code that we're using a CNC machining process. So that's a pretty simple way that in the past I've used CNC machines as 3D printers, and in the future I plan to use this machine as a very, very large format 3D printer for my prints that won't fit on my relatively small form factor 9x9 by 4.5 machine. As far as coolant goes, I've tried a variety of different coolants, none proper coolants per se. I've tried straight water, I've tried straight isopropyl alcohol, which is a bit unusual because a lot of people won't use it due to obviously health concerns from using an alcohol mist, in addition to just the health concerns of using a mister period, putting whatever kind of coolant you have into the air and potentially breathed by your operator. And this has created a kind of interesting debacle because when using isopropyl alcohol or ethanol as a coolant system, I was getting very, very excellent chip clearing, and there was almost no residual coolant with the mister on the surface of my like wood board that I used just to quickly fixture aluminum pieces down to. So because the vapor pressure of the alcohol is so high that it almost immediately comes off and within a couple minutes, also meaning that there's very little cleanup to do at the end of the job. But I eventually decided that I need to go to a proper coolant route, not only because of the health concerns but also the safety concerns of, well, you're misting something that's highly flammable and you don't want an explosion at the point of the CNC router if for any bizarre reason you hit something like a screw here or some kind of thing that's holding the machine together that's not aluminum but steel, therefore causing sparking and initiating something or further problems down the road. As far as coolant containment here, it's basically just one of these like $40 Home Depot filters. I have the wrench right here that I can store all my coolant in. So it just unscrews, I pull it up and down, and just store it on the back here, and it's pretty convenient. So the way I control all this is I have a regulator on my air compressor coming into this green hose here, and then there's a Y. So the regulator, the air compressor controls the pressure going directly right here to the bit. So this is just one of those cheap $10, $15 misters off of Amazon that you can buy. I'll be honest, they don't work very well. The lock line tends to leak. They don't put out the same pressure that you're putting in through the regulator. I mean, I'm still using like 50 feet a quarter-inch hose, which is absolutely restricting my flow, but not by the same amount that like I would see with just a regular like air blast gun, for instance. And then to ensure that I'm actually seeing liquid get down here as efficiently as I want, for instance, if I want something closer to simulating flood coolant, what I can do is open up this regulator here. And what that'll do is it'll allow a set amount of PSI into my filter cartridge, which is, of course, water and air tight, and it'll put that pressure above all of my coolant. thereby forcing that coolant up the straw. This is just like 3/16 OD coolant or fuel line rather, that then goes all the way to my bit and at a much higher rate. I also have a little fuel line valve that I can use to further regulate the amount of coolant coming directly onto my cutting tip. Of course, I'm only really using this when I'm doing something like a deep pass in wood. I'll just use air, or if I'm doing my normal 40 IPM, 5 thou depth of cut, and maybe slotting, for instance, in aluminum with an O-flute bit, then I'll just put the coolant on here with a sufficient amount with a 40 psi air blast to ensure that I'm sufficiently clearing the chips, keeping both the part cool, the chips hot, and also the tool bit cool to ensure that I'm getting maximal cutting quality that I can.